So good morning to all of you. In previous session where I discussed uh, LTI system characterized by constant coefficient difference equations. Okay, there we have seen how to represent the total response of the system in terms of zero input response and zero state response. Today we will be discussing solution of linear constant coefficient difference equations. Okay, so how to identify the solution of linear constant coefficient difference equation. So in previous session we have seen the total solution, okay, y of n is nothing but the sum of zero input response plus zero state response. This zero input response is also called as natural response or free response, while this zero state response is also called as forced response, right? So while identifying, so we are interested in identifying the solution of linear constant coefficient difference equation. We have seen the generalized form of, so we have seen in a previous session that the generalized form of difference equation or the linear constant coefficient difference equation can be given as, that is, summation k is equals to 0 to capital N a k y of n minus k, which is equals to summation k is equals to 0 to m bk x of n minus k. So this is the generalized form of difference equation. Okay, so this difference equation is used to represent the response or the input output relationship of the LTI system. So we are interested in identifying the solution of the given difference equation, which is in this given form, right? So given a linear constant coefficient difference equation as the input output relationship describing the LTI system, our objective is to determine an explicit expression for the output y of n. Okay, so we are interested in identifying the output y of n simply. Okay, so whatever method that we'll be looking here, how to identify the total solution, but to get the total solution we should know the zero input response and zero state response. But again, to identify zero input response you need homogeneous solution. From homogeneous solution you can identify zero input response, and then you can identify a particular solution. You can combine homogeneous solution and particular solution, and then you can identify the zero state response, and finally you will combine zero input response and zero state response to get the total response of the system. Okay, so whatever, so the method that we'll be looking for identifying this total solution, okay, in terms of homogeneous solution, then zero input response, homogeneous solution combined with particular solution, from it you can identify the zero state response, and then by combining zero input response and zero state response you will get the total solution. So this method is called as direct method. You can also use Z transform approach to identify these total response of the system, which is called as indirect method. Okay, so basically the goal is to determine output y of n for n greater than or equals to 0, okay, of the system given a specific input x of n for n greater than or equals to 0 and a set of initial conditions. So that means we will be identifying y of n, okay, for n greater than or equals to 0, okay, provided we have been provided with or will be provided with input x of n, okay, input x of n for n greater than or equals to 0 and some initial condition. Okay, so by using these set, that is the set of input and the initial conditions, right, you can identify the response y of n. So there are two methods. So first one is the direct method. Okay, so direct method you can identify the solution of given difference equation. Okay, so uh, we'll get the total response, that is y of n, by solving the given difference equation. Okay, so in direct method we solve difference equation get the total response of the system, right? So this difference equation represent the input output relationship of given system, discrete time system, or LTI system, DTLTI system. Okay, and second method is the indirect method, right, where you can use Z transform. Okay, so here the direct indirect method, we are identifying the total solution of the given difference equation, and basically the total solution is the sum of two parts. Okay, so you can say that this total solution in direct method is given as y of n is equals to yh of n plus yp of n. Okay, so it consists of two parts. So first part is called as homogeneous solution, second part is called as particular solution. In previous session we have seen total solution is the combination of zero input response and zero state response. Okay, so basically this y z I of n is identified by using yh of n. Okay, and yzs of n, that is, you can identify zero input response from homogeneous solution, and you can identify zero state response by using homogeneous solution plus particular solution, right? So the generalized form of this total solution comprises two parts, that is homogeneous solution and particular solution, right? So initially we'll look at the procedure how to identify homogeneous solution, then we'll see how to identify zero input response from the homogeneous solution, then we'll see how to identify particular solution, then we'll see how to identify zero state response by combining homogeneous solution and particular solution, right? So here this yh of n, okay, yh of n is called as what? Homogeneous solution, or it is also called as complementary solution. Okay, while this yp of n is called as particular solution. Okay. So basically you might have solved these difference equations in subject mathematics. Okay, there you have also computed the homogeneous solution and particular solution, right? So here we are using those difference equation to describe the characteristics of given LTI system by representing the input output relationship. So in subsequent session we will be identifying all these uh, procedures to identify the homogeneous solution, right, as well as particular solution. From homogeneous solution, how we'll see how to identify zero input response, right? Then we'll see by taking the combination of homogeneous solution and particular solution how to identify the zero state response. Okay, so now we'll see how to identify the homogeneous solution of a difference equation. Okay, the homogeneous solution of a difference equation. Okay, so how to identify this homogeneous solution? So while identifying this homogeneous solution, we begin the problem of solving linear constant coefficient difference equation, basically which has the generalized form as k is equals to 0 to n a k y of n minus k is equals to summation k is equals to 0 to m bk x of n minus k. Okay, So to get the homogeneous solution, we assume that input x of n is equals to 0, because from homogeneous solution we are identifying zero input response. Okay, so in previous session we are saying to identify the zero input response, you are considering input x of n is equals to 0. Okay, so homogeneous solution is identified by assuming that the input x of n is equals to 0. Okay, here we'll assume what x of n is equals to 0. Okay, so when we substitute this x of n, right, uh, in the given difference equation, right, so we'll get this difference equation, this given difference equation will get in this form, because we are substituting input x of n is equals to 0, so all the terms on right hand side will be 0. Okay, because we are considering all inputs as 0, right, so this term will be 0, right. So we are assuming x of n is equals to 0, or you can say that input is equals to 0 simply, right. So whatever input samples are there, we are assuming it as 0 to get the homogeneous solution. So the remaining equation will be k is equals to 0 to n ak y of n minus k is equals to 0. In previous session we have seen this capital N indicates the order of the difference equation. So it is the nth order difference equation, or you can uh, call it as nth order difference equation. Okay. So the procedure procedure for solving a linear constant coefficient difference equation is very similar to the procedure of solving linear constant coefficient difference equation. Okay. So the solution of this equation has the form, that is this homogeneous solution is given as yh of n is equals to lambda to the power n. Okay, so simply we'll try to substitute this value in this equation. Okay, so we'll get this equation as summation k is equals to 0 to n ak. In place of y of n minus k, we'll substitute lambda to the power n. So yh of n is equals to lambda to the power n. So y of n minus k, we'll get it as lambda to the power n minus k. Okay, is equals to 0. So this yh of n is equals to lambda to the power n is nothing but the form of the solution of homogeneous equation, or it is the generalized form of homogeneous solution simply, right. So we get this equation after substituting this value lambda to the power n in the given difference equation. Okay, so I'll rewrite this equation here. What we get here, k is equals to 0 to n ak lambda to the power n minus k is equals to 0. Okay, now if I'm substituting the values of k in this equation, okay, one by one, so I will get a0, right, lambda to the power n minus 0, that means lambda to the power n, plus a1 lambda to the power n minus 1, right. If I'm substituting k is equals to 1, so it will be a1 lambda to the power n minus 1 plus a2 lambda to the power n minus 2 plus and so on, plus the last value of k is capital N, so it will be an lambda to the power n minus n, right, is equals to 0. Okay, so here you can take this lambda to the power n minus n common, okay, from these terms. So if I'm taking this lambda to the power n minus n outside the bracket, so in bracket I'll get simply a0, right. So it will be simply a0 is lambda to the power n. I have taken lambda to the power n minus n common, so I'll get lambda to the power n, okay, in bracket, plus, so this basically lambda to the power n is simply the if you add this, if you multiply these two terms, that is lambda to the power n minus n multiplied by lambda to the power n, so it's uh, raised to the power will get added, so n minus n plus n. Okay, so this minus n plus n will be 0, simply small n will be there, right? Similarly, a1 will get lambda to the power capital N minus 1, right, plus a2 lambda to the power n minus 2 plus and so on plus an, okay, is equals to 0, right? So this basically, if you are transferring this again to right hand side, so it will be simply 0, 0 divided by this term will be 0, so remaining equation will be simply a0 lambda to the power n plus a1 lambda to the power n minus 1 plus a2 lambda to the power n minus 2 plus and so on plus an is equals to 0. And this a0, as we have seen in previous session, this a0 is equals to 1, okay, because the actual form of our generalized difference equation, whatever we have considered here, when you are substituting k is equals to 0, so it will be a0 y of n, okay, but the coefficient of y of n is generally 1, okay, so a0 is 1 here, right? So you can take it as 1 also. So the remaining equation will be lambda to the power n a1 lambda to the power n minus 1 a2 lambda to the power n minus 2, then plus and so on plus what is that, an is equals to 0, okay. So if I'm assuming this a0 as 1, so the remaining equation will be a to the power n plus a1 lambda to the power n minus 1 plus a2 lambda to the power n minus 2 plus and so on plus an is equals to 0, right? So I can solve this polynomial, nth order polynomial, okay. So it will have two roots, just for example x square plus 2x plus 1, so it will have it is the second order polynomial, okay. So it has two roots. In similar manner, it is lambda to the power n plus a1 lambda to the power n minus 1 plus a2 lambda to the power n minus 2 plus and so on plus an is equals to 0 is the nth order polynomial, and it has n capital N roots, right? So if we represent those roots as lambda 1 comma lambda 2 comma and so on comma lambda n, okay, so these n roots are represented as lambda 1 lambda 2 up to lambda n, okay. So you can, by solving this polynomial, you can identify these roots, right? So if we assume that the roots are distinct, okay, roots are distinct mean, so each root has different value, okay, so there is no same root, okay, or the root having same values, right? So if we are assuming that the roots are distinct, there are no multiple order roots, then the most general solution of the homogeneous difference equation, okay, is given as, that is, you can give as yh of n is equals to, we have seen the generalized form of homogeneous solution as lambda to the power n, okay, but here total n roots are there, lambda 1 lambda 2 up to lambda n, so you have to consider n constants, right? So those n constants will be, so just for example, if I'm considering c1 will be the first constant, so the first root is lambda 1, okay. Second constant I can consider c2, it will be lambda 2, right, lambda 2 to the power n, okay, because the generalized form of homogeneous solution we consider lambda to the power n, okay. So it will be c1 lambda 1 to the power n plus c2 lambda 2 to the power n plus and so on plus cn lambda n to the power n, okay. So that is the required homogeneous solution of the given difference equation. So what we have done, initially we have assumed the input as 0. After substituting input 0, we get some difference equation. In that equation, in place of y of n, you are substituting value lambda to the power n. So after substituting that value lambda to the power n, we will try to identify a polynomial from it. Okay, so how this value you have substituted, you have substituted value of k here, you have taken lambda to the power n minus n common. Okay, so you got this polynomial, and then nth order polynomial has been solved to get n number of roots. So this lambda 1, lambda 2 up to lambda n represent and roots. Okay, and capital N roots of the given nth order polynomial. Okay, so this is nothing but the nth order polynomial. Okay, so it has n roots. So after identifying those n roots, you can write down the homogeneous solution. Okay, so this is the required homogeneous solution. This is how you are identifying the homogeneous solution, right? So in this homogeneous solution, as there are capital N roots, so we have assumed capital N constants, that is C1, C2 up to Cn. Okay, so these C1 comma C2 comma up to Cn are nothing but the constant coefficients, or these are also called as weighing coefficients. Okay, these are also called as weighing coefficients. Okay, so these are basically constants. Okay, so these coefficients are determined, you can determine the values of the C1, C2 and Cn from the initial condition, okay, specified for the system, that is y of minus 1, y of minus 2 and so on, right? So you can use those initial conditions to get the actual values of these constants. Okay, but while identifying these constant, again you will be assuming input x of n is equals to 0, right? So uh, after identifying these values of c1, c2, cn, again you will substitute these values in the equation of homogeneous solution, and then that response, that homogeneous solution, will be simply called as zero input response, that is y z I of n. So to get this y z I of n, you need to identify the values of these constants. Okay, you need to identify the values of these constants. Okay, so how we will be identifying these constants? So simply again by considering whatever the initial conditions are given for the system. Okay, that is y of minus 1, y of minus 2. Okay, it depends how many initial conditions are there, right? And as well as by assuming input x of n is equals to 0. Okay, so after substituting these two things in the given homogeneous solution and the given input output equation, you can identify the zero input response. Okay, in next session we'll be discussing how to identify the homogeneous solution and the zero input response. Okay, so we'll be looking one problem, there we'll be identifying homogeneous solution and the zero input response for the given input output equation, or by utilizing the given difference equation. Okay, so in today's session we will discuss what is the basically the how total solution of the uh, difference equation is represented. Okay, so there are two methods, you can use direct method or indirect method. Okay, in subsequent session we'll be looking at the direct method, that is nothing but solving the difference equation, right? So total solution comprises two parts, that is homogeneous solution and particular solution. From homogeneous solution you can identify zero input response. From homogeneous solution and particular solution you can identify the zero state response. Okay, so here we have seen the procedure to identify the homogeneous solution. Okay, initially you will assume input is equals to 0. Okay, because from homogeneous solution you are identifying zero input response, so you will be considering input is equals to 0. And the generalized form of homogeneous solution is y h of n is equals to lambda to the power n. So that value will be submitted in the given difference equation. So after substituting that value In the given difference equation, you will get the nth order polynomial depending on the order of the difference equation, right? If it is a second order difference equation, so you will get second order polynomial. So depending on the order of polynomial, you will get number of roots. Okay, so in case of nth order polynomial, you will get n roots. In second order polynomial, you will get 2 roots. So depending on the roots, you will write down the homogeneous solution, okay, by assuming the constant c1 c2 up to cn, as there are n roots in this case, right? And then to get the zero input response, you will identify the values of these constants, that is c1 c2 up to cn. But to identify the value of these constants, again you will be considering input is equals to 0, and you will be substituting the values of initial conditions if those values are given, okay, in the problem, or it is specified for the given system, right? So in next session we'll be looking at how to identify the homogeneous solution from the given difference equation. Okay, so thank you for joining this session.